Hi everyone, I hope you're doing well today. This video lecture is discussing the notes and examples for section 4.7, graphing and inverse trigonometric functions. We're going to be defining the trigonometric inverse functions here graphically and also symbolically. Okay, so that we can evaluate expressions involving inverse trig functions. Later we're going to be using the inverse trig functions in order to find individual solutions to trigonometric equations. The inverse trigonometric functions are designed as functions themselves. And I want to remind you of the definition of a function, that a function is a rule which assigns exactly one output to each input value you find in the domain, right? So a function will only ever give you back one value, one number, right? So if we are building inverse functions, we're building them with the understanding that they themselves will be functions, and they can only give us one answer. But many equations that we have to solve actually have more than one answer to them. Take as an example the equation y equals x squared, right? Y equals x squared, which is itself a function, right? We can write the function f of x equals x squared and verify it is in fact a function for any value x that we plug in, okay? For any x that we plug in, okay, in the domain for this is all real numbers, negative infinity to positive infinity. There is only one, okay, there is only one value y that is the square of that x, right? So for example, if we choose, x is equal to 3, right, then x squared is equal to 9, and 9 is the only value that we would get out of the function, right? Hence this is a function because this would be true for any value we choose. A quick way to verify that something is in fact a function, okay, over its entire domain is in fact to look at the graph. Okay, if we know how to graph a relation, in this case we do, right? We know how to graph y equals x squared. It looks like a parabola. It goes through 0, 0 and 1, 1. It looks like this, right? The way to verify that this is in fact a function, okay, is by use of what's called the vertical line test. The vertical line test is based off of the definition of what makes something a function. That is, that we can choose any value in the domain. Choose any value in the domain. In fact, we want to do this for every value in the domain. Okay? And verify that it only intersects the graph at one point. So for example, if I choose an x value out here, then I can draw the vertical line. I can draw a vertical line through there. And what I'm checking to see is that for that value of x that I've selected, there is only one associated value of y from the graph. Okay, that's what verifies that this is in fact a function. Not to just check it here, but in fact to scan the entire curve from left to right so that any vertical line that I could select, okay, can only intersect the graph in one location. That is a graphical way to verify that a given relation is in fact a function, is by the vertical line test. It immediately follows from the definition of a function. Now an inverse function of a function that is called, let's say, y equals f of x, we're going to call the inverse function y equals f to the negative 1 of x. That's the notation we would use for an inverse function. The name of the function it's inverting is right here. This is the inverse of f. Okay? Note, this notation implies inverse. It does not imply reciprocal. Although something like x to the negative 1 means 1 over x, f to the negative 1 does not mean 1 over f. f to the negative 1 means notationally the inverse of f. And what we mean by inverse, okay, is that we can reverse the roles of input and output. So f inverse of x, okay, the inverse function to f, reverses the roles of input and output in the function f of x. So to demonstrate an example of that type, let's take this one right here. So let's take, for example, f of x equals 3x minus 2 as a given function. And we want to determine, is there an inverse, and what would that inverse be? Could we define f to the negative 1? Well, take a look at what f does to a value x, right? For any value x that we choose to plug into here, f is going to apply the following operations in the following order. For any x in the domain, okay, the function f will do the following. First, by order of operations, okay, it will multiply the given value of x by 3, right? That's the first thing we're going to do. For any value of x we plug in, we're going to multiply that by 3. Then, after that's complete, we are going to subtract 2 from the result. Now the question here for us with inverses is, if the inverse exists, it should allow us to reverse this process, okay? Reverse the order in the process and reverse the operations in the process. That's what we want f inverse to do. I hope we'll be able to demonstrate why we wanted to do that. Essentially, we want to build a function whose job is to solve this function for us. We want to solve for x, but we want to build a function that does the solving for us. So if it exists, f inverse will need to be constructed so that first it does, right, it have to reverse the order and the operations in order for this to work. So the first thing that f inverse would do, would be the opposite of this step. Instead of subtracting 2, it would have to add 2 to whatever value is being input into the inverse. Then it's going to have to do the opposite of this. So instead of, since the original function multiplied by 3, we're going to need the inverse to divide by 3. Symbolically, therefore, we could write f inverse of x as the function that first adds 2 to x, so that would be x plus 2, and then divides the result by 3. So this, x plus 2 over 3. That would be the inverse defined. Now, what is it that we're doing here? Why did we do that? We want to be able to solve this function for any value of the input. Okay, so let's take, for example, if we wanted to solve for when f of x, okay, for when f of x is equal to, let's say, let's make f of x equal to 7. Okay, solve f of x is equal to 7. That is, we are given an output of the function f, right? So according to the function f, this is a y value, right? This is a y value in terms of f of x, right? Okay, solve f of x is equal to 7. Now the normal way that we would be doing this is we would say, well, that means we're setting up the equation 7 equals 3x minus 2. And then what exactly do we do in order to solve this equation? The exact steps we take, notice, are to solve for x, that we will first, right, add 2 to both sides, right? The first step we're going to take is to add 2 to both sides. And the next step after we add 2 would be to divide by 3. Well, that is now encoded within the inverse function itself. And so this is what we're going to do. We're going to take the value of the output of the original function and make that output become the input of the inverse function, right? So the inverse function that we built, f inverse of x, we're going to plug into that inverse, right? The input of the inverse is going to be what was the output of the original function. So we're going to plug the number 7 into the inverse. And then the inverse is going to do the work of finding out what the value of x was that we should have used. Right? If we plug 7, right, the output of the original function, if it becomes the input of the inverse function, the inverse then does this, 7 plus 2 over 3, which equals 9 over 3, which is equal to 3. This number right here is the output, okay, the output of the inverse function. So according to the inverse function, when it looks at the 3, it sees what it thinks is a y value. But notice that that output right there is exactly the same number that we would have selected to plug into the original function. Right? So notice that f of 3, right, if we had plugged the 3 into the original function, we would get, right, 3 times 3 minus 2, which is 7, right? So we've solved the problem. We found out the value of x. For the original function, we found the value of x that would have given us the output. Okay? Now, this is all fine and good, and certainly a lot of hoops to jump through when we already knew how to solve this type of a problem, right? When we're dealing with more complicated, look at algebraic equations, like trigonometric equations, we're not just going to necessarily know what steps to take to solve the problem, but we're going to need to build operations that are designed to reverse or invert other operations, right? So for instance, what I'm saying is, we know that the opposite of multiplying is dividing. We know the opposite of subtracting is adding, okay? But the question is, what's the opposite of taking the sign of a number? And the answer to that would be, well, we have to build an operation that is the inverse of the sign. We have to design one, because we're not going to be able to cancel the sign with something like a logarithm or a square root, right? We need to build a function whose job is to cancel out the trigonometric function, right? So that we can solve trigonometric equations. And let's go back up here to this other function we had, this f of x equals x squared. Notice that if we wanted to solve, like we were doing just a moment ago, if we wanted to solve for a given output, right? If we wanted to solve like f of x is equal to some number, let's take a number that's convenient. Notice this, if we were trying to solve, let's say, f of x is equal to 9, that is, if we wanted to solve the equation x squared is equal to 9, right? If we had an inverse operation, okay, we would be able to find the value of x. But there's actually not one value of x that makes this equation true. There are two values of x that make this equation true, right? Solving this equation, notice that x equals 3 is a solution, or x equals negative 3 is a solution. That is to say, if we tried to build, okay, if we tried to build some inverse function, okay, some inverse function, f inverse, such that we plugged the 9 into it, okay, the problem here, okay, if this inverse was to be constructed to specifically, right, solve this equation, the problem here is that we have to allow this inverse to now give us what? 2 answers? We have to allow it to equal plus or minus 3. What's the problem there? That means that this thing would not be a function, but it's specifically supposed to be a function, right? We even gave it the name of a function, right? So the problem here, okay, is that when the output of an original function, okay, when the output can be associated to more than one possible input, we have to choose, of all the possible solutions we could have gotten, we have to choose one of those solutions as the principal solution, and then working with that principal solution, we can build a function, okay? So what we do when we're solving the equation x squared is equal to 9, right, what key is it on your calculator that you hit to solve this equation, right? You would go to the square root key, okay? The square root key, okay, the square root key is a function key, okay? If you define f inverse of x to be the square root of x, okay, so that the square root is the opposite of squaring, if you plug the 9, the output of the x squared equals 9 into it, right, you get the square root of 9. If you check on your calculator, the square root of 9 is always going to equal 3. it never equals -3. Even though -3 was a solution to the equation we were interested in, the key on the calculator, hence the function that is designed to invert the square, okay, is designed to only ever give us one output because it is a function. And that one output that it's giving us is the principal solution. Okay, it's one of potentially many solutions is what we are saying a principal solution is. For the case where it's an x squared is equal to 9, there's in fact two solutions, 3 and -3, but the only one we can get from the calculator would be 3. It's up to us, by our knowledge of the function, the squaring function, and its symmetry, for instance, like we can use its graph, to know that there's in fact more than one solution to this particular equation. Okay? When you have a function that when set up compared to a certain output has more than one possible solution, we declare that the function is not invertible, and we have to make an adjustment to the function so that it is invertible. The characteristic I'm referring to here is that for every one input, there is only one output, and for every one output, there could have only been one input. It's called 1-to-1. Okay, it's called 1-to-1. We need to make this function here 1-to-1. We need to make it 1-to-1. In order for us to be able to have a function key, right, so that we can find at least one solution. As soon as we have one solution to this equation, we can then extend upon that and find the other solutions. But when we go to our devices, like our calculators, the calculator is only designed to give us one of the solutions, and we have to figure out what the rest are in general. Okay? All right. So 1-to-1. How do we define better what 1-to-1 is? Well, 1-to-1 would be basically a prediction that the inverse will be a function itself. That is, if we did the job of switching the input and the output with each other, okay, the result of that would also give us a function. We can define 1-to-1 by taking the definition of a function itself and replacing output with input and input with output. If we switch what is the output with what is the input, right? That's what we did symbolically over here. If we had the output to a given function, we plugged that output into the inverse function if we had it. Okay? So a function is a rule that assigns exactly one output for each input. Well, then a 1-to-1 function would be one that assigns exactly one input for each output. That is, that a function is 1-to-1 if you plug in a y value and can get only one possible x value. Right? A function is called 1-to-1 if for any y value you plug in, there was only one x value you could have had. Okay? And that's if it already was a function to begin with as well. The way we check that graphically is by doing the reverse of the test that we used to see if something was a function, right? We said that something is a function if vertical lines only intersected it once. That's because every vertical line is us choosing a value of x. Okay? Now, if we want to check to see if something... Right. If we want to check to see if a given function might be 1-to-1, i.e. invertible, we can design what is called a horizontal line test. The horizontal line test, okay, is designed off of the definition of 1-to-1. It's saying if we were to select a y value, that is to draw a horizontal line, that is us choosing a y. If we notice that it intersects the graph in more than one location, then it is not 1-to-1, right? This curve here fails the horizontal line test. For example, if we choose the horizontal line where y is equal to 9 on the graph of y equals x squared, it will intersect the curve at two locations. One of those locations would be associated to where x is equal to 3, because 3 squared is equal to 9. And the other location would be where x is negative 3, right? Each of these points represents solutions to the equation whereby the output of the function is equal to this y value here. Okay. If a graph of a function passes the horizontal line test, we declare that the function is 1-to-1. If the graph of a function does not pass the horizontal line test, then the function is not 1-to-1. So how do we build an inverse when the function is not 1-to-1? Okay, the answer to that would be we restrict the domain of the function. In this case, we choose, of these solutions we could get, we choose one of them to be the principal solution. And for this, for y equals x squared, we choose the principal solution to be this one right here. Okay? And we're going to focus on that one as if it was the only, the only real solution for the inverse. Okay? And we eliminate the rest of the curve over here. Okay? So we have restricted the domain. We just restricted the domain of the function f of x equals x squared such that x is greater than or equal to 0. By making that restriction, the graph now suddenly passes the horizontal line test, and since it passes the horizontal line test under this restriction, we can therefore declare it to be 1-to-1 and create an inverse function. So we can invert the squaring function, building a square root function, under the understanding that it only works, we can only apply that square root, okay, we can only apply that square root if we say that the answer is only ever going to be a positive number or 0. Okay, so using the graphs of given functions, we can really quickly analyze whether an inverse exists over the entire function. Okay, that's using the horizontal line test. Okay, if it passes the horizontal line test already, then you're good to go. You can build an inverse. But if it does not pass the horizontal line test, you need to find a restriction in the domain such that you would cover the entire range of all the possible outputs, okay, but you still pass the horizontal line test. All right, so we want to do that with our trigonometric functions. If the trigonometric functions pass the horizontal line test, we got nothing to worry about. We'd be fine. But if you think of the graphs that we've already done for the trigonometric functions, think of those wave functions, the sine and cosine waves, and think of the tangent function, the way it looks. If you extend it out to negative infinity and positive infinity, those graphs do not pass the horizontal line test. So restrictions on the domains are going to be required. This vitally means also that when you go to your calculator to hit the key on your calculator that is supposed to solve trigonometric equations for you, I'm talking about the inverse trig keys, just like when you go to your calculator to hit the square root key to solve this equation here, you're not going to get the full story. Your calculator is only going to give you one answer called the principal answer, the principal solution. Okay? Right, so anytime, for example, in an algebra class or beyond, if you're ever given the equation x squared is equal to 9, and if you write the solution to that as x equals 3, and that's it, you would always get marked wrong because you missed an entire solution. If you rely too heavily on the calculator to just do this for you, the calculator doesn't know, it just gives you the principal solution and that's it. Okay, but we have to know that the calculator is only telling us one solution that is related to the other solutions that we also need to determine. In the same way, when we're solving trigonometric equations, the calculator can only take us so far. It can only take us to one solution, if any at all, a principal solution. And then we're going to use symmetry, that would be the reflective and the periodic symmetries that we've already previously discussed, in order to see how the one solution the calculator can give us can be used to determine a reference number for all of the other solutions that also would have been true to the given equation. Let's take a look at an example of like a basic trigonometric equation. Let's just say I wanted to solve the equation the sine of theta, okay, is equal to 0. That equation right there, okay? Now, that is to say, if we had the function f of theta is equal to the sine of theta, first off, that's a function because its graph passes the vertical line test, but is it invertible? That's how many solutions do we actually have to this equation, right? Let's take a look at the graph, okay, for f of theta is equal to the sine of theta. So I'll make this the theta axis right here, okay, the theta axis, and of course the sine of theta, right, is this wave, right? It extends outward like this and it goes out towards infinity. All right, so when is the sine of theta equal to 0, right? If the output, okay, the output is 0, okay, that would occur here and here and here and here and here, here, right? How many solutions do we actually get to this equation, okay? If we draw the horizontal line with the equation y equals 0, how many times does it intersect the curve? Does the curve f of theta equals sine theta pass the horizontal line test? And the answer to that would be no. It fails miserably, right? The horizontal line test, okay, determining whether this function is invertible, any horizontal line we draw can only cross the graph at most one time in order to pass the test. How many times does it cross here? Infinitely many times. We have infinitely many solutions. Okay, there are an uncountable number of solutions to this equation. Of all of the solutions that there are to this equation, okay, if we can think of any one of those solutions, we can then use the symmetry of the sine function, the symmetries, right? There's odd symmetry, right? So a kind of reflective rotational symmetry that we have, right? And there's also periodic symmetry, which is the repeated behavior. We can use symmetries on any one solution we can find to determine all the other solutions as well. So we already know some of the solutions. Some of the solutions to this equation right here would be theta is equal to 0, or theta is equal to pi, or 2 pi, okay, or 3 pi, or 4 pi, and right, this would be 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, on and on and on. And how about the other direction? There would also be solutions at negative pi, negative 2 pi, negative 3 pi, negative 4 pi, etc., etc., etc. Right? There's an infinite amount of these, and we can combine all those into an infinite set of solutions. But here's what I want to talk about here for today. Right? How do we solve this using the calculator? And the answer to that would be the calculator has a function programmed into it called the arcsine function. F inverse of x, okay, is sine to the negative 1 of x. It is the arcsine function, or called the inverse sine function. The arcsine is designed, this is not reciprocal, this does not mean cosec, it's not 1 over, right? This is the notation for inverse. It is designed to tell us, okay, a principal value, okay, that would be a solution of this equation. Okay, if we were to plug in to this 0, that is, if we were to plug the output of the original function, right? If the output of the original function was plugged in, 0 was the output of f of theta, not the input, right? It was the output. Okay, if we plug that into this inverse function and then go to the calculator and we ask the calculator what is the arcsine of 0, the calculator, okay, the calculator's principal solution that it will give us will be 0. Graphically, what's happening is the calculator is looking at this solution. Amongst all the solutions we could have given, this is the solution that the calculator will tell us. And it's going to leave it up to us to determine that all those other solutions even existed. Okay? The calculator is programmed to do this in the following way. The graph of the function that we're asked to invert does not pass the horizontal line test. So what we do, okay, is we restrict the domain in such a way where we can cover the entire range of possible outputs of the function, okay, but we still pass the horizontal line test, okay, and that restriction, okay, I'll put that restriction inside like a green box here maybe, okay, that restriction on the domain is going to focus in on this portion of the graph only, okay, and it's going to ignore all the stuff that happens outside of that box. That is, the restriction that is selected is from this point to this point on the sine curve, right? It's just this region right here. That would be from negative pi over 2 to positive pi over 2. In this way, whenever you use the arcsine function, okay, either on the calculator or any other software or by hand, if you are talking about using this function, the answer, okay, the output that you get will always be contained within the interval negative pi over 2 to positive pi over 2. Right. And that is done so that the key, the arcsine key itself, is a function. If this restriction was never done, then this would not be a function key, okay, which would be problematic. Principal solution, okay, comes about by a result of an agreed upon restriction on the domain of the original function in order to get it to pass the horizontal line test, right? By focusing in on this little box right here from negative pi over 2 to pi over 2, we get a graph that does pass the horizontal line test, and the only point within this box, right, that is associated with an output of 0 is that point right there, and that point right there has an input of 0, so 0 becomes the only solution that matters here, the principal solution. Okay, then, when we're solving these trigonometric equations in a later section, we're not doing solving trigonometric equations just yet. When we're solving these in a later section, we're going to take the principal solution that we can find by this manner, and we're going to use symmetry in order to figure out all the other solutions from that. Okay, right now we're just working on building these inverse functions. So I give you a worksheet whereby you can go through, okay, follow the instructions I give you on the worksheet that I designed for you so that you can see how to invert and describe the inverses of the main trigonometric functions, the inverse of sine, cosine, and tangent. I give you a dotted curve representing the entire function, in this case the y equals sine x extending out forever, but I give you, using a solid curve, I give you the restricted, okay, the restricted function that would be 1-to-1, right? It passes the horizontal line test if we only consider this portion that has a solid curve, right? I would note that there are other choices we could have made. I mean, we could have chosen to go from this point to this point as the solid curve and said, well, that would have been 1-to-1 as well. That's true. This selection right here, from negative pi over 2 to pi over 2 for the sine function, okay, is noted as being the principal branch. Okay, it is the most commonly chosen invertible restriction of the original sine function, and it is most commonly chosen anytime we might hit an arcsine key or call the arcsine function. Okay, so the domain that we have selected, the restriction for the sine function we've already declared is negative pi over 2 to positive pi over 2. That's what I'm asking for here. Right? What is the range of that restricted piece? In fact, it's the same as the range of the whole function. That is, from the lowest y value to the highest y value, the range would be from where y is -1 at the bottom to where y is +1 at the top, from the minimum to the maximum in this case. Quadrants refers to what quadrants in the unit circle would these solutions be associated with. As a result of the restriction, the answers, the outputs of the arcsine will always be between negative pi over 2 and positive pi over 2. In the unit circle, these quantities right here, okay, are found in which quadrants, okay, in the unit circle? if this is 0 right here, that's where theta is equal to 0. Okay, note that theta is equal to pi over 2 up here, and theta is equal to negative pi over 2 is down here. Right? So if we are saying that we are between negative pi over 2 and pi over 2, okay, that is a bracket right there, right? From negative pi over 2 to pi over 2, that means we're going to find solutions always in quadrant 1, right? In quadrant 1 and quadrant 4. So the choice of the restriction on the sine function has as a consequence of it that we will always be finding solutions to the arcsine in quadrant 1, okay, and quadrant 4. So the quadrants would be quadrant 1 and quadrant 4 for the sine function. Right? Now what about for the cosine function? What domain have we selected here for the cosine function? Okay, notice the solid portion of the curve right here. It goes from x is equal to 0 until x is equal to pi, right? So the choice that we make principally for the cosine function would be to restrict the domain from 0 to pi. Right? We restrict y equals the cosine of x, okay, to a domain from 0 to pi, including the 0 and the pi, so that we end up with a graph, okay, a restricted graph that just looks like this, right? It's that portion of the cosine wave. It goes as high as 1, right, where y is equal to 1, and as low as negative 1. Right, here we have the x-axis, we have the y-axis. This passes the horizontal line test under this restriction. Okay, what quadrants would we end up being in if we're saying that the that the restriction on the input here was 0 to pi? 0 to pi, in other words, are associated in the unit circle to which quadrants? Okay, theta is equal to 0 would be right here. Theta is equal to pi would be right here. And to be between 0 and pi would mean that we are somewhere along this portion, the upper half of the unit circle. That would mean that we're in either quadrant 1 or quadrant 2 for any principal solution that we get, okay, by using the arccosine. So for example, let's say we wanted to solve, okay, we'll do more solving trigonometric equations in the future, right? But as a preliminary example here, let's say we wanted to solve the equation the cosine of theta is equal to, let's say, negative root 2 over 2. Okay, the cosine of theta is equal to negative root 2 over 2. Okay, if you go to your calculator and you enter into your calculator the arccosine of negative root 2 over 2, the answer that it's going to give you is going to be the principal solution, right, taken from this restriction. That is, right, remember that in the unit circle, the x-coordinate is the cosine, right? Remember that, right? So the x-coordinate is the cosine. So if the cosine is negative root 2 over 2, then that means that the x-coordinate is negative root 2 over 2. Well, that happens in quadrant 2. And the quadrant 2 solution, the value of theta, okay, associated with that quadrant 2 solution that is between 0 and pi, would be 3 pi over 4. This is the solution the calculator is going to give you when you input arccosine of negative root 2 over 2. The actual, though, the set of solutions for the cosine of theta is equal to negative root 2 over 2 actually has an infinite number of solutions. Right? The calculator is going to give us the principal solution. The principal solution that is given to us is always going to be in the interval from 0 to pi. If you hit the arccosine key, if you want to invert the cosine, right, then the choice that we make principally is that our answers will be between 0 and pi. Right? That's what we're saying. It is because we had to make some selection of some branch here that passed the horizontal line test. That's why it's designed that way. Okay, same thing is done with the tangent function. The tangent is a wave that repeats and repeats, right? It has no amplitude to this wave. It goes up to infinity, down to negative infinity, right? But the principal branch is chosen to be this right here. Okay, so inverting the tangent function, if we wanted to invert the tangent function, let's say I call it f of x equals the tangent of x, we are going to restrict the domain to be between negative pi over 2 and pi over 2. And notice that I'm using parentheses here. Okay, parentheses. This is an open interval. And that's because we have vertical asymptotes at negative pi over 2 and pi over 2. Okay? For the sine and the cosine, we used brackets on the restriction because those endpoints were included. But for the tangent, right, we keep parentheses because it's an open interval because we have asymptotes there. Now, if we take only this solid wave right here and ignore or erase all the other waves, all the dotted ones, notice that this restriction on the tangent gives us a graph that passes the horizontal line test, so it is all of a sudden invertible. Okay, we can then use that in order to evaluate, arctangent expressions. Okay, so let's say I wanted to know what is the arctangent of 1. What is the arctangent of 1? What I'm saying is, for what angle theta would the tangent of that theta be equal to 1? That's if the input, okay, if we see that the input of the inverse function is exactly the same as the output of the function it's inverting, right? The output of the tangent function was the input, okay, of the inverse function, right? For what theta is the tangent of theta equal to 1? In fact, there's an infinite amount, okay? There's an infinite amount of solutions to this equation. But we want specifically the solution to this equation such that theta is between negative pi over 2 and positive pi over 2. And the only solution to this equation between negative pi over 2 and pi over 2 would be pi over 4. That is, that we know that the tangent of pi over 4 is equal to 1. All right, graphing functions. Well, to graph inverse trig functions, okay, you do this same thing that we do when we're building the inverse trig functions. It's all about switching input with output is what we're doing. Okay, so if we know, for instance, from here, if the domain of the sine function, the restricted domain, was that x is between negative pi over 2 and pi over 2, then the range of its inverse would have to be where y is between negative pi over 2 and pi over 2. We literally take the x values of the original function and make them the y values of the inverse, and vice versa. Let's take a look at some examples here of some things maybe you have to do in your homework as well. Okay, we have lots of examples of this type that we could work on. How about evaluate the arcsine of 1/2? How do we do that? Okay, well, consider the equation sine of theta is equal to 1/2. Consider this equation. That would be the inverse for this equation right here. We can interpret this geometrically in a couple different ways. One way we can interpret it geometrically is by using the right triangle trigonometry. Right? We can draw a right triangle. Right? We can draw a right triangle with an angle theta in it, such that the sine of that theta is equal to the ratio 1/2. Right? With SOHCAHTOA, that would mean that we have an opposite side equal to 1 and a hypotenuse side equal to 2. Right? And in order to evaluate this expression here, what we're doing is we're evaluating the arcsine of 1/2, which is going to equal the theta, right? If we take the arcsine of both sides of this equation, we would get this equation, right? Just like if we had the squaring function x squared is equal to 9, we can apply the square root to both sides. In this case, if we wanted to solve for theta, we can apply the inverse of sine to both sides of the equation, right? So we would be evaluating the expression, okay, by setting the expression equal to theta and then inverting it. Okay, that's how we're going about it. Now, what is an angle theta okay, that we can use as a reference or a principal solution here that we already know would fit inside of this triangle. And one such solution to that would be pi over 6. In fact, there's an infinite amount of solutions to this equation, but there's only one output to this that would be correct, and that would be pi over 6. Okay? Or 30 degrees. Right? So the arcsine of 1/2 is equal to pi over 6 because, right? Because the sine of pi over 6 is equal to 1/2. Right? The input of the arcsine we have just considered to be the output of the sine function because those functions are inverses of each other. Okay? And pi over 6, okay, is specifically a number between negative pi over 2 and pi over 2. That's why the arcsine outputted that as the only number, okay, that this could evaluate as. All right, let's take a look at a composition. Letter D. Evaluate. Now, the secant of the arcsine of 1/5. How to do this? Consider the inverse trig function is equal to, like we just set up above, the inverse trig function, okay, is equal to, let's say, theta. All right? Then inverting that, we would see that the sine of theta is equal to 1/5. And we don't want to know what theta is in this case. What we want to know, okay, in order to evaluate this then, if we said the arcsine of 1/5 is theta, then what we're actually evaluating is the secant of theta. Okay, but we don't need to know what theta is to do that. Okay, instead we can use the right triangle trigonometry, right? The arcsine of 1/5 is equal to theta, meaning the sine of theta is equal to 1/5. And by right triangle trigonometry, that means there would be a right triangle with an angle theta in it, such that the opposite side is 1 and the hypotenuse is 5. Now the question is, what is the secant of that theta? Right? If we find the secant of theta, we would have the secant of the arcsine of 1/5, because the arcsine of 1/5 is theta. Right? Now the secant of theta is found by taking the hypotenuse divided by the adjacent, right? It's the reciprocal of cosine, okay? The hypotenuse is equal to 5, but the adjacent is something we need to solve for. Let's call the adjacent right now x. Let's solve for it by the Pythagorean theorem. X squared plus 1 squared is equal to 5 squared. That is, x squared is equal to 25 minus 1, which is 24. So x is equal to the square root of 24, right? That's a principal square root of 24 because x has to be positive because it's a distance. And that simplifies as 2 square root of 6. So the adjacent side is 2 root 6. So back to our secant of theta. The secant of theta is 5 over 2 root 6. And that's where our solution comes from. So we never actually found out what theta was equal to. Okay? We used theta so that we could invert the inverse trig function back into a standard trig function. And we used right triangle trigonometry, okay, SOHCAHTOA, and the identities, like the reciprocal identity that we know for secant, right, in order to actually go about and evaluate this. The secant of the arcsine of 1/5, which is the same as the secant of theta with the triangle that we constructed, is 5 over 2 root 6. Or if we rationalize the denominator, okay, we can say this is 5 root 6 over 2 times 6 is what? 12. And there's the solution. So the secant of the arcsine of 1/5 is equal to 5 root 6 over 12. Okay, that's where that solution is coming from. Now, in the same way, we're going to be able to evaluate expressions that are not going to give just numerical values. Okay, we're going to use the same technique in order to evaluate all of these expressions right here, to transform them into algebraic expressions in x. Okay, let's try this one right here. The cotangent of the arcsine of x. I'm going to apply the same technique that we just used a moment ago. Take the inverse trig function and set it equal to theta. Okay, then invert that, we get the sine of theta is equal to x. Now use right triangle trigonometry. If we draw a right triangle, okay, and put an angle theta in our right triangle, we need to associate side lengths such that the sine of theta is equal to x. Well, x can be written as the ratio x over 1. So the sine of theta is equal to x over 1. We can set that the opposite side is x and the hypotenuse side is 1. Now what we're evaluating, since the arcsine of x is equal to theta, we're actually now evaluating the cotangent of theta. What is the cotangent of theta? Okay, the cotangent of theta is the reciprocal of tangent. Okay, tangent is opposite over adjacent, so cotangent is adjacent over opposite. Okay, notice we don't need to know what theta is. We don't need theta as an angle. We want the cotangent of theta. Now, adjacent and opposite. Well, we already know what the opposite is. The opposite to theta is x, so we know the denominator will be x. But what is the adjacent side? Let's call this y for right now and use the Pythagorean theorem to find out what y equals. Y squared plus x squared is equal to 1 squared. Solve for y. That means y squared is equal to 1 minus x squared. So y is equal to the principal square root of 1 minus x squared. Again, only the principal square root because y must be positive, right? It's a distance. So the adjacent side is the square root of 1 minus x squared. Right? The cotangent of theta is equal to the square root of 1 minus x squared over x, right? And that's exactly the answer that we have on the, on the worksheet that we were going for. That's not right. That's my square root symbol right there. That's how we did. The process was take the arc function, set it equal to theta, invert it to get a basic trig function. Use right triangle trigonometry to draw a picture of a right triangle associating the numerator and denominator of the output of this, right? To get that ratio of sides. And then evaluate the original function by use of that substitution for theta, okay? Which may have to require that we use the Pythagorean theorem in order to solve the triangle. Example, okay? I'm doing a lot of arcsines here. Let me do one that has something different. How about do this one right here. The sine of the arcsecant of x over 3. The sine of the arcsecant, or the inverse secant, of x over 3. Alright, we set the inverse trig function, arcsecant of x over 3, set that equal to theta, and then invert it. That is, therefore, the secant, right, this is the arcsecant of x over 3, therefore the secant of theta is equal to x over 3. And let's represent that then with a right triangle. Alright, we can draw a right triangle with an angle theta in it. Okay, secant is the reciprocal of cosine, right? So this is going to be the hypotenuse over adjacent, right? So the hypotenuse of our triangle can be x, and the adjacent side can be 3. Now what we want to evaluate is the sine of theta, right? Because we said the arcsecant of x over 3 will be theta. So what is the sine of theta? Well, the sine of theta is opposite over hypotenuse. Okay, now we already have the hypotenuse, that's x, right? We have to figure out the opposite. Let's call that y for right now. Solve for y. Well, 3 squared plus y squared is equal to x squared. Right? 3 squared plus y squared is equal to x squared. That is, right, y squared is equal to what? X squared minus 9. And hence y is equal to the principal square root of x squared minus 9. So the opposite side, okay, is the square root of x squared minus 9. So the sine of theta is the square root of x squared minus 9 over x. So the original expression, the sine of the arcsecant of x over 3, okay, by this process, right, this is equal to right, the square root of x squared minus 9 over x. Okay, and that's the answer we were looking for. Okay, that's the answer we got here. All right, so this is some complicated stuff to get used to here. Okay, give it a try in your homework. Study the notes. Okay, it's okay if it takes some time to get used to it. Okay, it is quite difficult and challenging to do this material right here. We need these inverse trig functions so that we can later solve trigonometric equations, which is the final major objective we have in the course. We still have to talk about identities in Chapter 5, and then we'll be solving equations in Chapter 6. Okay, I'll be checking my email to see if there's any questions. Bye now.